Hi, everybody. Welcome to Stanford CS224N, also known as Ling 284, Natural Language Processing with Deep Learning. I'm Christopher Manning, and I'm the main instructor for this class. So what we hope to do today is to dive right in. So I'm going to spend about 10 minutes talking about the course, and then we're going to get straight into content for reasons I'll explain in a minute. So we'll talk about human language and word meaning. I'll then introduce the ideas of the word-to-vec algorithm for learning word meaning. And then going from there, we'll kind of concretely work through how you can work out objective function gradients with respect to the word-to-vec algorithm and say a teeny bit about how optimization works. And then right at the end of the class, I then want to spend a little bit of time giving you a sense of how these word vectors work and what you can do with them. So really the key learning for today is I want to give you a sense of how amazing deep learning word vectors are. So we have this really surprising result that word meaning can be represented, not perfectly, but really rather well by a large vector of real numbers. And, that's sort of in a way a commonplace of the last decade of deep learning, but it flies in the face of thousands of years of tradition and is really rather an unexpected result to start focusing on. Okay, so quickly, what do we hope to teach in this course? So we've got three primary goals. The first is to teach you the foundations, i.e. a good deep understanding of the effect of modern methods for deep learning applied to NLP. So we are going to start with and go through the basics and then go on to key methods that are used in NLP, recurrent networks, attention, transformers, and things like that. We want to do something more than just that. We'd also like to give you some sense of a big picture understanding of human languages and what are the reasons for why they're actually quite difficult to understand and produce, even though humans seem to do it easily. Now, obviously, if you really want to learn a lot about this topic, you should enroll in and go and start doing some classes in the linguistics department. But nevertheless, for a lot of you, this is the only human language content you'll see during your master's degree or whatever. And so we do hope to spend a bit of time on that starting today. And then finally, we want to give you an understanding of an ability to build systems in PyTorch for some of the major problems in NLP. So we'll look at learning word meanings, dependency parsing, machine translation, question answering. Let's dive into human language. Once upon a time, I had a lot longer introduction that gave lots of examples about how human languages can be misunderstood and complex. I'll show a few of those examples in later lectures. But since right for today, we're going to be focused on word meaning, I thought I'd just give one example, which comes from a very nice XKCD cartoon, and that isn't sort of about some of the sort of syntactic ambiguities of sentences, but instead it's really emphasizing the important point that language is a social system constructed and interpreted by people. And that's part of and it changes as people decide to adapt its construction. And that's part of the reason why human languages are great as an adaptive system for human beings, but difficult as a system for our computers to understand to this day. So in this conversation between the two women, one says, "Anyway, I could care less." And the other says, "I think you mean you couldn't care less. Saying you could care less implies you care at least some amount." And the other one says, "I don't know. We're these unbelievably complicated brains drifting through a void, trying in vain to connect with one another by blindly flinging words out into the darkness. Every choice of phrasing, spelling and tone and timing carries countless signals and contexts and subtext and more. And every listener interprets those signals in their own way. Language isn't a formal system. Language is glorious chaos. You can never know for sure what any words will mean to anyone. All you can do is try to get better at guessing how your words affect people, so you can have a chance of finding the ones that will make them feel something like what you want them to feel. Everything else is pointless. I assume you're giving me tips on how you interpret words because you want me to feel less alone. If so, then thank you. That means a lot. But if you're just running my sentences past some mental checklist so you can show off how well you know it, then I could care less." Okay, so that's ultimately what our goal is to how to do a better job at building computational systems that try to get better at guessing how their words will affect other people and what other people are meaning by the words that they choose to say. So an interesting thing about human language is it is a system that was constructed by human beings. And it's a system that was constructed, relatively recently in some sense. So in discussions of artificial intelligence, a lot of the time, people focus a lot on human brains and the neurons buzzing by and this intelligence that's meant to be inside people's heads. But I just wanted to focus for a moment on the role of language. There's actually, this is kind of controversial, but it's not necessarily the case that humans are much more intelligent than some of the higher apes like chimpanzees or bonobos, right? So chimpanzees and bonobos have been shown to be able to use tools to make plans. And in fact, chimps have much better short-term memory than human beings do. So relative to that, if you look through the history of life on Earth, human beings developed language really recently. How recently, we kind of actually don't know because, there's no fossils that say, okay, here's a language speaker. But, most people estimate that language arose for human beings sort of, somewhere in the range of 100,000 to 1 million years ago. Okay, that's a while ago, but compared to the process of evolution of life on Earth, that's kind of blinking an eyelid. But that power of communication between human beings quickly set off our ascendancy over other creatures. So it's kind of interesting that the ultimate power turned out not to be having poisonous fangs or being super fast or super big, but having the ability to communicate with other members of your tribe. It was much more recently, again, that humans developed writing, which allowed knowledge to be communicated across distances of time and space. And so that's only about 5,000 years old, the power of writing. So in just a few thousand years, the ability to preserve and share knowledge took us from the Bronze Age to the smartphones and tablets of today. So a key question for artificial intelligence and human-computer interaction is how to get computers to be able to understand the information conveyed in human languages. Simultaneously, artificial intelligence requires computers with the knowledge of people. Fortunately, now our AI systems might be able to benefit from a virtuous cycle. We need knowledge to understand language and people well, but it's also the case that a lot of that knowledge is contained in language spread out across the books and web pages of the world. And that's one of the things we're going to look at in this course, is how that we can sort of build on that virtuous cycle. A lot of progress has already been made, and I just want to very quickly give a sense of that. So in the last decade or so, and especially in the last few years with neural methods of machine translation, we're now in a space where machine translation really works moderately well. So again, from the history of the world, this is just amazing, right? For thousands of years, learning other people's languages was a human task which required a lot of effort and concentration. But now we're in a world where you could just hop on your web browser and think, oh, I wonder what the news is in Kenya today. And you can head off over to a Kenyan website and you can see something like this, and you can go, and you can then ask Google to translate it for you from Swahili. And, the translation isn't quite perfect, but it's, it's reasonably good. So the newspaper Tuko has been informed that local government minister Lingson Belakanyama and his transport counterpart Siddiq Mia died within 2 separate hours. So, within 2 separate hours is kind of awkward, but essentially we're doing pretty well at getting information out of this page. And so that's quite amazing. The single biggest development in NLP for the last year, certainly in the popular media, was GPT-3, which was a huge new model that was released by OpenAI. What GPT-3 is about and why it's great is actually a bit subtle, and so I can't really go through all the details of this here. But it's exciting because it seems like it's the first step on the path to what we might call universal models, where you can train up one extremely large model on something like that library picture I showed before, and it just has knowledge of the world, knowledge of human languages, knowledge of how to do tasks, and then you can apply it to do all sorts of things. So no longer are we building a model to detect spam, and then a model to detect pornography, and then a model to detect whatever, foreign language content, and just building all these separate supervised classifiers for every different task. We've now just built up a model that understands. So exactly what it does is it just predicts following words. So on the left, it's being told to write about Elon Musk in the style of Dr. Seuss. And it started off with some text, and then it's generating more text. And the way it generates more text is literally by just predicting one word at a time, following words to complete its text. But this has a very powerful facility, because what you can do with GPT-3 is you can give it a couple of examples of what you'd like it to do. So I can give it some text and say, I broke the window, change it into a question, what did I break? I gracefully saved the day, I change it into a question, what did I gracefully save? So this prompt tells GPT-3 what I'm wanting it to do. And so then if I give it another statement like I gave John flowers, I can then say, GPT-3, predict what words come next, and it'll follow my prompt and produce who did I give flowers to. Or I can say, I gave her a rose and a guitar, and it will follow the idea of the pattern and do who did I give a rose and a guitar to. And actually, this one model can then do an amazing range of things, including many that's quite surprising to do at all. To give just one example of that, another thing that you can do is get it to translate human language sentences into SQL. So this can make it much easier to do CS 145. So having given it a couple of examples of SQL translation of human language text, which I'm this time not showing because it won't fit on my slide, I can then give it a sentence like, how many users have signed up since the start of 2020? And it turns it into SQL. Or I can give it another query, what is the average number of influencers each user subscribed to? And again, it then converts that into SQL. So GPT-3 knows a lot about the meaning of language and the meaning of other things like SQL and can fluently manipulate it. Okay, so that leads us straight into this topic of meaning and how do we represent the meaning of a word? Well, what is meaning? Well, we could look up something like the Webster Dictionary and say, okay, the idea that is represented by a word, the idea that a person wants to express by using word signs, etc. The Webster's dictionary definition is really focused on the word idea somehow, but this is pretty close to the commonest way that linguists think about meaning. So that they think of word meaning as being a pairing between a word, which is a signifier or symbol, and the thing that it signifies, the signified thing, which is an idea or thing. So that the meaning of the word chair is the set of things that are chairs. And that's referred to as denotational semantics, a term that's also used and similarly applied for the semantics of programming languages. This model isn't very deeply implementable. Like, how do I go from the idea that, okay, chair means the set of chairs in the world to something I can manipulate meaning with in my computers? So traditionally, the way that meaning has normally been handled in natural language processing systems is to make use of resources like dictionaries and thesauri. In particular, a popular one is WordNet, which organize words and terms into both synonym sets, words that can mean the same thing, and hypernyms, which correspond to is-a relationships. And so for the is-a relationships, we can kind of look at the hypernyms of panda, and panda is a kind of procyonid, whatever those are. I guess that's probably with red pandas, which is a kind of carnivore, which is a kind of placental, which is a kind of mammal, and you sort of head up this hypernym hierarchy. So WordNet has been a greater resource for NLP, but it's also been highly deficient. So it lacks a lot of nuance. So for example, in WordNet, proficient is listed as a synonym for good. But maybe that's sometimes true, but it seems like in a lot of contexts it's not true, and you mean something rather different when you say proficient versus good. It's limited as a human-constructed thesaurus. So in particular, there's lots of words and lots of uses of words that just aren't there, including anything that is sort of more current terminology, like wicked is there for the wicked witch, but not for more modern colloquial uses. Ninja certainly isn't there for the kind of description some people make of programmers, and it's kind of impossible to keep up to date. So it requires a lot of human labor. But even when you have that, it has sets of synonyms, but doesn't really have a good sense of words that mean something similar. So fantastic and great means something similar without really being synonyms. And so this idea of meaning similarity is something that would be really useful to make progress on, and where deep learning models excel. Okay, so what's the problem with a lot of traditional NLP? Well, the problem with a lot of traditional NLP is that words are regarded as discrete symbols. So we have symbols like hotel, conference, motel, our words, which in deep learning speak, we refer to as a localist representation. And that's because if you in statistical or machine learning systems want to represent these symbols, that each of them is a separate thing. So the standard way of representing them, and this is what you do in something like a statistical model, if you're building a logistic regression model with words as features, is that you represent them as one hot vectors. So you have a dimension for each different word. So maybe like in my example, here are my representations as vectors for motel and hotel. And so that means that we have to have huge vectors corresponding to the number of words in our vocabulary. So the kind of, if you had a high school English dictionary, it probably had about 250,000 words in it. But there are many, many more words in the language really. So maybe we at least want to have a 500,000 dimensional vector to be able to cope with that. Okay, but the even bigger problem with the discrete symbols is that we don't have this notion of word relationships and similarity. So for example, in web search, if the user searches for Seattle Motel, we'd also like to match on documents containing Seattle Hotel. But our problem is we've got these one-hot vectors for the different words. And so in a formal mathematical sense, these two vectors are orthogonal, that there's no natural notion of similarity between them whatsoever. Well, there are some things that we could try and do about that, and people did do about that before 2010. We could say, hey, we could use WordNet synonyms and we could count things that list the synonyms as similar anyway, or hey, maybe we could somehow build up representations of words that have meaning overlap, and people did all of those things, but they tended to fail badly from incompleteness. So instead, what I want to introduce today is the modern deep learning method of doing that, where we encode similarity in a real valued vector themselves. So how do we go about doing that? Okay, and the way we do that is by exploiting this idea called distributional semantics. So the idea of distributional semantics is, again, something that when you first see it, maybe feels a little bit crazy, because rather than having something like denotational semantics, what we're now going to do is say that a word's meaning is going to be given by the words that frequently appear close to it. J.R. Firth was a British linguist from the middle of last century, and one of his pithy slogans that everyone quotes at this moment is, "You shall know a word by the company it keeps." And so this idea that you can represent a sense for words' meaning as a notion of what context it appears in has been a very successful idea, one of the most successful ideas that's used throughout statistical and deep learning NLP. It's actually an interesting idea more philosophically, so that there are kind of interesting connections. For example, in Wittgenstein's later writings, he became enamored of a use theory of meaning. And this is, in some sense, a use theory of meaning. But whether it's the ultimate theory of semantics, it's actually still pretty controversial. But it proves to be an extremely computational sense of semantics, which has just led to it being used everywhere very successfully in deep learning systems. So when a word appears in a text, it has a context, which are the set of words that appear nearby. And so for a particular word, my example here is banking, we'll find a bunch of places where banking occurs in texts, and we'll collect the sort of nearby words as context words, and we'll say that those words that are appearing in that kind of muddy brown color around banking, that those context words will in some sense represent the meaning of the word banking. While I'm here, let me just mention one distinction that will come up regularly when we're talking about a word in our natural language processing class. We sort of have two senses of word, which are referred to as types and tokens. So there's a particular instance for word. So there's, in the first example, government debt problems turning into banking crises. There's banking there, and that's a token of the word banking. But then I've collected a bunch of instances of quote unquote the word banking. And when I say the word banking, and a bunch of examples of it, I'm then treating banking as a type, which refers to, the uses and meaning the word banking has across instances. Okay, so what are we going to do with this distributional models of language? Well, what we want to do is we're going, based on looking at the words that occur in context as vectors, that we want to build up a dense, real-valued vector for each word that in some sense represents the meaning of that word. And the way it will represent the meaning of that word is that this vector will be useful for predicting other words that occur in the context of this. So in this example, to keep it manageable on the slide, vectors are only 8-dimensional, but in reality, we use considerably bigger vectors. So a very common size is actually 300-dimensional vectors. Okay, so for each word, that's a word type, we're going to have a word vector. These are also used with other names. They're referred to as neural word representations, or for a reason that will become clearer on the next slide, they're referred to as word embeddings. So these are now a distributed representation, not a localist representation, because the meaning of the word banking is spread over all 300 dimensions of the vector. Okay, these are called word embeddings because effectively when we have a whole bunch of words, these representations place them all in a high-dimensional vector space, and so they're embedded into that space. Now, unfortunately, human beings are very bad at looking at 300-dimensional vector spaces or even 8-dimensional vector spaces. So the only thing that I can really display to you here is a 2-dimensional projection of that space. Now, even that's useful, but it's also important to realize that when you're making a 2-dimensional projection of a 300-dimensional space, you're losing almost all the information in that space, and a lot of things will be crushed together that don't actually deserve to be better. All the making of that space at looking at 300-dimensional vector spaces or even 8-dimensional vector spaces. So the only thing that I can really display to you here is a 2-dimensional projection of that space. Now, even that's useful, but it's also important to realize that when you're making a 2-dimensional projection of a 300-dimensional space, you're losing almost all the information in that space, and a lot of things will be crushed together that don't actually deserve to be better. So here's my word embeddings. Of course, you can't see any of those at all, but if I zoom in and then I zoom in further, what you'll already see is that the representations we've learnt distributionally do just a good job at grouping together similar words. So in this sort of overall picture, I can zoom into one part of the space. It's actually the part that's up here in this view of it, and it's got words for countries. So not only are countries generally grouped together, even the sort of particular subgroupings of countries make a certain amount of sense. And down here, we then have nationality words. If we go to another part of the space, we can see different kind of words. So here are verbs, and we have ones like come and go are very similar. saying and thinking words, say, think, expect, they're kind of similar and nearby. Over in the bottom right, we have sort of verbal auxiliaries and copulars, so have, had, has, forms of the verb to be. And certain contentful verbs are similar to copular verbs because they describe states. He remained angry, he became angry. And so they're actually then grouped close together to the verb to be. So there's a lot of interesting structure in this space that then represents the meaning of words. So the algorithm I'm going to introduce now is one that's called Word2Vec, which was introduced by Tomasz Shmikalov and colleagues in 2013 as a framework for learning word vectors. And it's sort of a simple and easy to understand place to start. So the idea is we have a lot of text from somewhere, which we commonly refer to as a corpus of text. Corpus is just the Latin word for body, so it's a body of text. And so then we choose a fixed vocabulary, which will typically be large, but nevertheless truncated, so we get rid of some of the really rare words. So we might say vocabulary size of 400,000, and we then create for ourselves a vector for each word. Okay, so then what we do is we want to work out what's a good vector for each word. And the really interesting thing is that we can learn these word vectors from just a big pile of text by doing this distributional similarity task of being able to predict well what words occur in the context of other words. So in particular, we're going to iterate through words in the text. And so at any moment, we have a center word, C, and context words outside of it, which we'll call O. And then based on the current word vectors, we're going to calculate the probability of a context word occurring given the center word according to our current model. But then we know that certain words did actually occur in the context of that center word. And so what we want to do is then keep adjusting the word vectors to maximize the probability that's assigned to words that actually occur in the context of the center word as we proceed through these texts. So to start to make that a bit more concrete, this is what we're doing. So we have a piece of text, we choose our center word, which is here into, and then we say, well, have a model of predicting the probability of context words given the center word. And this model will come to in a minute, but it's defined in terms of our word vectors. So let's see what probability it gives to the words that actually occurred to the context of this word. It gives them some probability, but maybe it'd be nice if the probability it assigned was higher. So then how can we change our word vectors to raise those probabilities? And so we'll do some calculations with into being the center word, and then we'll just go on to the next word, and then we'll do the same kind of calculations and keep on chunking. So the big question then is, well, what are we doing for working out the probability of a word occurring in the context of the center word? And so that's the central part of what we develop as the Word2Vec. objective.
So what it is trying to do is this word is there, right? It will try to predict what is the probability of this word given banking is there, this word given banking is there, this word given banking is there, and the window size will be something like m, I guess, yeah, minus m to m. So from here minus m can, let's say, minus 2, so turning into, and plus m, cries and as, and for each of the word it will do, and then we are doing minus log likelihood. That's what we learned there, which checks if that how far each of these probability is from 1, because it is appearing in the context of that, in the likelihood of that, and all of those values should be equal to 1. But it will be something like 0.35, but that has to be 1. So we take that loss function, we backpropagate, and again try to reduce the error and everything, and that way the weights and everything, all of those we take into account.
So this is the overall model that we want to use. So for each position in our corpus, our body of text, we want to predict context words within a window of fixed size m given the center word wj. And we want to become good at doing that. So we want to give high probability to words that occur in the context. And so what we're going to do is we're going to work out what's formally the data likelihood as to how good a job we do at predicting words in the context of other words. And so formally that likelihood is going to be defined in terms of our word vectors, so they're the parameters of our model, and it's going to be calculated as taking the product of using each word as the center word, and then the product of each word in a window around it of the probability of predicting that context word in the center word. And so to learn this model, we're going to have an objective function, sometimes also called a cost or a loss, that we want to optimize. And essentially what we want to do is we want to maximize the likelihood of the context we see around center words. But following standard practice, we slightly fiddle that. We see essentially what we want to do is we want to maximize the likelihood of the context we see around center words. But following standard practice, we slightly fiddle that. Because rather than dealing with products, it's easier to deal with sums. And so we work with log likelihood. And once we take log likelihood, all of our products turn into sums. We also work with the average log likelihood. So we've got a 1 on t term here for the number of words in the corpus. And finally, for no particular reason, we like to minimize our objective function rather than maximizing it. So we stick a minus sign in there. And so then by minimizing this objective function, j of theta, that counts as maximizing our predicted accuracy. Okay, so that's the setup, but we still haven't made any progress in how do we calculate the probability.
Let's do this for today itself. Let's keep it till here.